Hello, Jonathan Broadwell with Broadwell Consulting Incorporated, and today we're going to take a look at the serial Wombat 18AB chip scaled output capability. And this is going to be the first video in a series on the scaled output capabilities and the third video in our robot series, because we're going to be using the scaled output capability on a servo pin mode in order to control the robot arm. The scaled output set of services are a set of services that are available on the serial Wombat 18AB proportional outputs. And essentially, this is how we take the input from one pin or the input from a PC and control an output through a series of transforms. So we get our source data. This happens potentially every 1 millisecond or at a rate that can be configurable by the user. We get our input data, and that could either be a value that's written to our pin by the host, the Arduino, the PC, the MicroPython board, whatever, or it could be data that we pull from another pin, like a frequency reader or an analog input or something like that. In any case, we get a number that comes in that ranges from 0 to 65,535. And then either output scaling is enabled, in which case we pass through this path, or it's not enabled, in which case the input value goes directly to the output value and is output. So for a servo, this could be a pulse width. For a PWM, it could be a PWM percentage. So for the example today, we're going to look at the limits on our robot arm. Each of the servos is capable of moving through about 180 degrees, but that doesn't mean that the robot arm is capable of moving in that amount of space. You know, for instance, the gripper may only move through a fraction of the servo's possible movement. The elbow is capable of hitting itself in one direction. And so we don't necessarily want to enable those servos to be able to drive across their full range, because we don't want the robot parts banging into themselves. So we're going to be taking a look at the scaled output, and essentially we will have a piece of data right now that comes in from the PC. We will enable scaled output. So that piece of data, which ranges from 0 to 65,535, our minimum to our maximum, whatever that might mean, will flow through here. And we're going to set for right now each of these boxes disabled until we get to scale output. So our value that comes in from the PC will just pass through each of these boxes and go to scaled output. So at this point, scaled output will get a value from 0 to 65,535. And what we're going to do within this box is provide a set of scaling so that for each location on the robot, that corresponds to a 0 to 65,535 for the full range of that particular joint. Okay, so for our first example, we're going to look at the gripper servo, which is on pin 18. And we've configured this servo, and we can see as we move it back and forth, we get to a place where, okay, that's as far as it can open, but that's not the limit of the servo's motion. So we start pushing against the servo, trying to drive it open even farther. And I know from experience that this particular gripper can actually get stuck if you drive it to that edge really, really hard. So as we look through this, 0, the closed location, happens at about 42,000. So we're going to set a limit on there of 42,000. So if we start a spreadsheet here, we have our gripper on pin 18. And the raw value that we're seeing, we're going to say 42,500. And the result of that is closed. And then if we come back here and go back the other way, we can see that we get a maximum open at 9,700. So those will be the scaled values. And we said before that we want closed to be 0. So eventually we'll use the reverse function of the serial Wombat chip, but we'll do that later. Let's take a look at the wrist rotation next. And that's on pin 17. But in order to be able to rotate that wrist, we're going to have to configure pin 15 in order to be able to hold it up so that we can see the rotation. And so if we go back to pin 17 now, we can see that one direction gets us all the way clockwise, looking out of the arm. The other direction gets us all the way counterclockwise. And it looks like the servo is allowed to move through its full range of motion. So for that one, for the wrist rotation, we will keep that at 0 to 65,535. Now let's take a look at the wrist up and down. And in order to do that, we're going to have to lift the elbow a little bit so that we can get full motion. And so the elbow is on 15. And so we will lift them up there. And now let's take a look at the full range on 16. Okay, so as I move the wrist around, it appears that I can get to about right here before my current really jumps, indicating that I'm blocked. So we will mark that one as 20,700. And in the opposite direction, how far can we go? And do we need to lift that wrist a little farther? And let's try that. Yeah, it looks like we have the full range of motion up to 65,535. So we will keep that at that. Okay, now let's take a look at the elbow, which is on pin 15. We know that it looks like we can move to the edge of the servo there. So for the elbow, 15 and 0. And in order to test it in the other direction, we're going to have to lift the shoulder, which is on pin 14. And it appears that I can't quite get enough torque on that to make that go. Oh, I need to configure the servo. There we go. Whoop, that's getting a little wild there. Okay, so let's bring that guy down now. And again, we'll experiment with the elbow, which is on pin 15. And at this point, we're down, so we can bring the shoulder up a little farther. Go back to pin 15. How far can we go? Again, bring the shoulder up a little farther. And if you want to know why robotics is hard and why there's companies that sell software that costs an enormous amount to figure out how to make a robot move through space, you can see it, because it is complicated figuring out how to make the robot move without hitting itself. And let's go ahead and move the wrist out a little bit. That's on pin 17. Oh, I'm sorry. It's on pin 16. Okay, I'm going to move the shoulder up even a little higher. And I'm going to move the elbow up a little bit. And let's take a look again at the wrist and see what we can do there. Okay, that's the limit right there. So it looks like the limit on that one is actually at the high. So if we take the pin number 15 and move it all the way back, we have full range of motion on that particular servo. Okay. Now let's take a look at the shoulder, which is on 14. It's a little bit out of the view of the camera, but it appears that I can go all the way to 65,535 without maxing out current. And again, on this one, now we're going to have to play with the elbow to get some room to move. Let's grab the wrist, which is on 17. I'm sorry, 16, I think. Okay, we heard it hit on metal, and we don't want that. So it looks to me like the minimum we should do here is about 6,000. You could break things pretty easy there. So yeah, we could, actually the whole thing just quit. I'm going to put this guy back where he was and power up the robot one more time. Okay. And it's doing its best to get up there, but it doesn't have quite enough torque. So we're going to have to move that lever around in a little bit. Yep, there we go. Yeah, things are getting wild. Trying to drive those servos as far as we can, and physics is getting in our way a little bit. Okay, so let's see if we can point this arm pretty much straight up. And now we'll take a look at the last servo, which is number 13, which is the shoulder rotation. Okay. And we can see there is a metal plate that he can hit against right there. And so our minimum, again, we'll put that in at 6,000. Shoulder rotate, servo 13, 6,000 goes all the way counterclockwise, looking out of the arm. And if we go the other direction, I'm sorry, that should be clockwise, going out of the arm. And on that one, I'm not getting any current pull, so we can go all the way to 65,535. So we have all of our limits here. And so I'm going to go in here and I'm going to enable output scaling, the output scaling module, and I'm going to plug in these values, 6,000 and 65,535, and say configure output scaling. Now if I come back here, you can see that we run, and it's not as visible on this one as it will be on some of the others, we run beginning to end without hitting our edges. So now let's look again at pin number 14. Which we said we want to limit to 6,000 and 65,533. And now if we move that one, and again, I can't quite do it here. So let's put this down and let's do one that's a little bit more obvious, like the elbow. The elbow, actually, we're going to leave alone. That had full range of motion. The wrist is a good one. So that's on servo number 16. So we'll go over here to output scaling. And I did this one wrong. We're going to go to output scaling and set 6,000 to 65,535 on the shoulder. And then we will go up to the wrist, which is number 16. And on our output scaling here, we will put that one at 20,700 to 65,535. Enable it and configure the output scaling. Now, if we go to the position controller now, the value it feeds in, what we can see is that I can move across the entire range without hitting my edges because I'm scaling it within the serial Wombat chip. And same thing, we will go to wrist rotation. That one doesn't need to change because it can go full range. And the gripper, this is maybe the most clear one. And let me rotate the arm so that you can see it clearly. We will go to the gripper, which is on pin 18. And we will set those values on the output scaling to 6,000. I'm sorry, gripper is 9,700 and 42,500. So when we do that now, if I go all the way down there, we open, and 65,535 is closed. Now, real quick, let's take a look at the invert. We're going to say invert input, and because we said we wanted 0 to be closed, and you can see now when I go to 0, it's closed. When I go to 65,535, it's open to the max. But we can see, and you can't see the current supply on the display, but we're not hitting the edges. We're not hitting that current limit. So that, in a nutshell, is how you use the output scaling. Again, the idea is that the full physical range of the device gets scaled to 0 to 65,535. So that's all for this particular example. We'll look in the future at how to program this into Arduino or Python, and we will also look next at rate limiting. The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features. The Serial Wombat open source project was created by Broadwell Consulting Incorporated. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Also, feel free to leave your question in the comments below.